AI has pretty much disrupted the way scientists and engineers look at many areas, including signal processing problems. Today's lecture is one attempt to steer your thoughts towards AI in the context of signal processing. My main message in this lecture is that AI is capable of learning some of the classical algorithms that we've already developed in this course. And on top of that, in many practical settings, AI can do much better than classical algorithms, for instance, the linear minimum mean square error estimator that we already saw in the last lecture. So, here is a summary of today's lecture, and let's get started with the prerequisites first. The prerequisites here are just a repetition of some of the concepts that we've already covered in the last lectures. Okay, the first prereq is on LMMSE estimation, which is the shorthand notation for linear minimum mean square error estimation. Today I'm going to explain LMMSE using an example that we will use throughout this lecture. This is also something that I covered in the Q&A session of lecture 18. So let's say we want to measure the temperature in a city, denoted by little a, and the statistics associated with this temperature is given by normal with mean 0 and variance sigma square. Okay, so this statistics is defined by the random variable capital A over here. Okay, so this is a kind of a city whose temperature swings about 0 degrees both in the positive and the negative directions with equal probabilities. That's something that we already know about the normal distribution, right? Now, to measure the temperature of this city, let's say I mount two thermometers at two distinct locations in the city. Thermometer 1 gives out a measurement x1 and thermometer 2 gives out x2. The random variables associated with these measurements are capital X1 and capital X2, say. The problem that we had looked at in lecture 18 is to determine the minimum mean square error estimate of the temperature condition on the observed measurements small x1 and small x2, right? This estimator, as you know, is the expected value of the random variable capital A, which models the temperature realizations, condition on the pair of observations x1 and x2, right? Further, I also discussed in the Q&A session last week that the MMSE estimator is linear whenever the random variables are jointly Gaussian. Clearly, in this case, the random variables x1, a, n1, x2, and n2 are jointly Gaussian. And in this case, the LMMSE estimator, which also turns out to be the MMSE estimator, is given by this equation over here. Okay, so the coefficients highlighted in brown represents the weight that sit in front of the measurements x1 and x2. Okay, now let me give you a very quick interpretation to this equation. Let's consider a scenario where the noise variance at thermometer 1 is substantially higher than that at thermometer 2. In this case, sigma 1 square is higher, so 1 over sigma 1 square is smaller. And the LMMSE estimator simply assigns a lower weight in front of x1, right? Now this makes intuitive sense because if the thermometer 1 is crappy, equivalently sigma 1 square is higher, then there's no point in assigning a higher weight before x1, right? Now let me give you another insight into the LMMSE estimator. Now let's say we want to measure the temperature of a city, and let's say we know that the temperature doesn't vary much about the mean 0, okay? And let's consider the extreme case where sigma square, which models the spread of this distribution of temperature of the city, goes down to 0. So when sigma square goes down to 0, you can notice that the coefficients of the LMMSE estimator, that weigh x1 and x2, go down to 0, right? And this makes intuitive sense because if I know for sure that the temperature outside is going to be 0 with a very high probability, then there's no point in measuring the temperature with thermometer devices that are noisy, right? So in this case, A hat LMMSE is 0 when sigma square approaches 0, okay? So in this lecture, we are going to see how AI can learn this intelligent LMMSE estimator that maintains a good balance between the prior and the measurements. Okay. The next prerequisite is on map detection. MAP stands for maximum a posteriori probability. And this is something that we've already learned in the last lecture, right? So let's say we are interested in detecting the presence of a target signal S of n. So this detection problem comes in the context of radars, okay? And it also comes in the context of detecting faults in a gearbox without even opening the gearbox. So if you remember in lecture 5, I discussed about how we could detect such faults by simply sticking an accelerometer to the exterior of this gearbox, right? Okay. So to solve the signal detection problem, we formulated two hypotheses, H0 and H1, within the framework of hypothesis testing. So under hypothesis H0, the received measurements are simply realizations of a noise process W of n, and under H1, the other hypothesis, the measurements are the sum of the target signal S of n and the noise realizations. Okay. The map rule, which we developed in the last lecture, simply minimizes the probability of error for the given statistical model. So let's say we know the a priori probabilities P1 and P0. Here P1 is the probability that the target signal is going to be present, and P0 is the probability that the target signal is absent, okay, or no target signal. Okay. The idea underlying map rule is to first compute the prior times the likelihood under each hypothesis H0 and H1. So the products that we compute here are proportional to the a posteriori probability actually. So if you notice, we have P1 times F R given H of the observation vector conditioned on H1, right? So that's proportional to the a posteriori probability under the hypothesis H1. And similarly, you have the quantity on the right defined for hypothesis H0, okay? Now, if the product associated with H1 is higher than that with H0, the map detector declares that hypothesis H1 is true. And in the other case, the map detector declares H0 to be true. On further simplification of this map rule, we ended up with a linear inequality based rule, okay, where the term on the left is just a linear function of the received measurements, right? So in a practical setting, we know what S is. We also know sigma square, okay? It's the variance of the measurement noise. And let's say we also know P0 and P1, okay? We just plug in all of these terms into this equation. And in real time, when we get the received measurement vector, the collection of R's, we just plug that in into this equation. And based on the term on the left and right, so if the term on the left is higher, we declare H1, and in the other case, we declare H0. Okay, so the map detector for the special case of additive white Gaussian noise samples is simply a linear inequality. Okay, today we are going to see how AI can learn this map detector. Okay, and finally, the last prereq that I'm going to talk about is basic gradient descent that you've already encountered in your undergrad. Let's say we want to minimize a cost function C over two deterministic variables W and B. For example, this function can model cost function in economics or a system related function in engineering that we want to minimize by tweaking these parameters W and B. These parameters are typically called as the optimization variables in your problem. The way to solve this problem could be using gradient descent, which is a very simple iterative algorithm that starts with an initial guess on W and P. Let's say we are at W0, P0. Then in every iteration, gradient descent updates W and P to move it in the opposite direction of the gradient. Okay, so we compute the gradient at each point and move in the opposite direction of the gradient. Okay. Now these iterations are performed successively until a convergence criterion is met. Okay. Now, assuming that the function is smooth and the step size is small enough, it can be shown that gradient descent drives WP to the minima, that is W of P out. I discuss gradient descent here because it lies at the very core of many AI algorithms. Okay. Note that the step size over here needs to be positive and the gradient descent equations are shown over here. So the next iterate of the optimization variables W and P is the current iterate minus eta, which is the step size, times the gradient. Okay. Now, that said, let's move on to the next section of today's lecture, which is on motivation for AI. In this section, I'm going to give you a sense of what is AI and answer these key questions. First, why do we want to use AI? And second, what makes AI a big reality today that is deployed in many systems around us? Let's say I give you a signal R of t shown over here, and I tell you that this signal is a noisy version of a sinusoid. And the question here is to sketch the denoise version of the signal R of t. One way to find the underlying sinusoid is to look out for the zero crossings and get an estimate of the time period. Then look at the signal values around the maxima and minima to estimate the amplitude. Once we have estimates of the amplitude, the phase, and the time period, sketching this sinusoid is a very trivial problem. So let's just think for a moment how we were able to sketch out the denoise version of the signal R of t. We were able to do that because we understand the underlying structure of sinusoids. From a layman's perspective, we as humans use our intelligent brains to accomplish complicated tasks, and sketching out the denoise version of a sinusoidal signal is one basic task. Now, machines can do something very similar using what we call as artificial intelligence, AI. AI algorithms first learn the structure of sinusoids using a large data set, and then they use this learned information to denoise the signal. With such an algorithm, a noisy sinusoid gets in and a cleaner sinusoid comes out. A good algorithm is one that denoises a signal that is not even in the dataset that is used to train the AI model. You might wonder now, why do we need AI as we could have performed denoising with classical signal processing? Well, the answer is that many practical problems are much more complicated than simply denoising sinusoids. For example, we may not even have proper mathematical models that define a problem. And in cases where we do have such mathematical models, classical techniques may be intractable. In the next few slides, I'm going to give you some concrete examples highlighting these scenarios where classical techniques fail. In lecture 19 on signal detection, we've seen that diabetes diagnosis is a solved out problem. We have very well defined mathematical models for the biomarker used to diagnose diabetes. In this case, it's the glucose level, right? And then we could use map detection to figure out whether a person has diabetes or not, just using the measured glucose level, let's say R. The real challenge in healthcare is not about diagnosing diabetes. Rather, it's about predicting the onset of diabetes in future. Many big companies in healthcare analytics are interested in this problem of predicting diabetes onset. This is a very interesting problem in my opinion because if we identify upfront that someone might develop diabetes, we can recommend, say, lifestyle changes that can potentially delay the onset of diabetes. The big question now is, how do I solve this interesting problem? This is a hard problem because we just don't know the complete set of biomarkers for diabetes prediction. For example, what is a good set of R for this problem? And what is a good measurement model for the biomarkers under different hypotheses in the context of diabetes prediction? These are questions that are still unclear. And what is the noise statistics? Let's say when we measure each biomarker. All these problems are something whose answers are unknown, and you can easily see that the map detection is almost impossible in this context of diabetes prediction, right? Now, when we lack such proper mathematical models to solve a problem, we could go with a data driven approach based on AI. A possible way to solve the diabetes prediction problem is to start off with a massive clinical campaign. Let's say we approach millions of people who do not have diabetes this year in 2022, and let's say we acquired data on their glucose levels, stress levels, genetic history, diet, and age. Okay, and 5 years down the line, let's say we test the same cohort for diabetes. So all those in red over here ended up with diabetes, and those in green are diabetes free in 2027. Okay, now we turn our time machine back, and based on the biomarkers in 2022 and the future state of people in 2027, let's say we train an AI model that predicts the onset of diabetes. Okay, and suppose a big company takes up this interesting project and obtains a well trained AI model. Now, this model can be used in 2027 to predict the chance of a person acquiring diabetes 5 years down the line, that is in 2032. And this prediction is just based on the biomarkers in 2027. Of course, this model assumes that the biomarkers shown over here are sufficient enough to predict the onset of diabetes. And on top of that, we also assume that this model assumes time invariance. Okay, that is the same model trained on the 2022 dataset applies for the 2027 dataset as well. Okay, the time invariance, in my opinion, is reasonable as I don't see any reason why it should not hold. Next, I'm going to talk about another classical problem that we've seen in lecture 18, which is MMSE estimation. So let's go back to the temperature example that I just discussed. This time we've got to estimate temperature using measurements from just one thermometer instead of two. And in this setting, the true temperature is modeled as a realization of, say, a uniformly distributed random variable between minus 10 degrees and 10 degrees. As we've seen in the last lecture, finding a closed form expression for the MMSE estimator in this case is hard. And the primary reason that we were unable to figure out a closed form expression for the MMSE estimator is that the integral in this case turned out to be intractable. And that happened because A is uniformly distributed between minus 10 to 10, right? So as a compromise, what one could do is to restrict the class of estimators to a linear one and figure out that linear estimator that minimizes the mean square error. And that's something called as a LMMSE estimator, right? Now, a different approach that turns out to be better than LMMSE estimation is to use AI. In this approach, we could simulate several realizations of temperature measurements and then train an AI model to estimate the true temperature. So, xk, that is the measurement that comes out from the thermometer, gets into this AI model, and this AI model spits out an estimate ak hat. Okay. Now this ak hat is compared with the true temperature ak, which is available in the dataset, in order to fine tune the AI model. And at the end of this fine tuning stage, we expect that when we deploy this AI model in practice, this model can take a look at the temperature estimate that comes out from the thermometer, and we expect that this model should give out a temperature estimate A hat that's close enough to the true temperature. Okay. Now, although some of the key ideas underlying AI were discovered a couple of decades ago, today AI is a big reality due to these four major things. First, we are able to build advanced sensors that can collect massive amounts of data and relay them to a central server through wireless connectivity. My group here in the Dell Center for Systems and Control develops algorithms and solutions that efficiently connect sensor nodes in a wireless network or base stations or mobile stations. Okay. Second, memory has become so cheap that we are able to store information at a very low cost. Okay. For example, 10 centimeter long CDs developed a decade ago could just store a few hundred megabytes. Today, we are able to store a few gigabytes in just the size of a chocolate. Okay. And these memory devices can be used to store the massive amounts of data that we collect from sensing networks. Third, engineers have been developing advanced AI algorithms that can solve complicated tasks that were simply unimaginable few decades ago. For instance, Gmail can predict the subsequent portion of my sentence when I'm typing in, and I find that really cool. There are also other interesting applications such as autonomous cars, personal AI assistants, and robots that can navigate by themselves. All of these interesting applications of AI have made our lives much easier. Finally, computing has become much cheaper than what it was earlier, and it's also even more accessible. For instance, you could train a very complicated AI model over the cloud, say using Amazon Web Services. And once you've trained the model, you can import this trained model onto your mobile device and perform inference or execute real time computations on this AI model on your low computation mobile device. Okay. So, all of these four factors have made AI a big reality today, and it has now become a hot topic that attracts attention from the industry as well as academia. So, in this portion of the lecture, I'll discuss a quick overview of the basics underlying AI. Then, I will talk about the notion of perceptron within AI and show you how perceptrons can learn the MMSE estimator as well as the map detector. Sounds cool, right? So, let's check this out. Here is a slide that introduces AI and machine learning, the two buzzwords in today's world. As we discussed earlier, AI is all about machines accomplishing tasks that we humans carry out using our intelligence. Machine learning is how a machine develops this artificial intelligence. In general, machine learning includes supervised learning, unsupervised learning, and reinforcement learning. Defining all of them, of course, is beyond the scope of this lecture. So today, we are going to focus on supervised learning, which fine tunes models over training data to yield desired output. For example, a supervised learning model can be trained over a large dataset of labeled handwritten digits. A well trained model, in fact, can even figure out a new handwritten digit that doesn't even have a label. Cool, right? So, for the purpose of this lecture, I'm going to assume that AI is equivalent to supervised learning using neural networks. This makes my life much easier because I don't need to say that I'm talking about supervised learning using neural networks each time. I'm just going to say, here is an AI algorithm, and it should imply in this lecture that this means supervised learning using neural networks. Okay, so that said, let me minimize my video over here so that the slides look less dense in the subsequent portion of the presentation that's more mathematical in nature. Okay, so let's get started with the basics of AI first. A neural network is basically a graph with several nodes called neurons, which are these little bubbles shown over here. The links between the neurons are the connections in a neural network, and this architecture is pretty much inspired by the way neurons in our brain are engineered. The perceptron is the simplest form of a neural network where n number of input neurons are connected to a single output neuron as shown over here. The perceptron functions as follows. Real valued scalars x1, x2 and so on up to xn get into the perceptron and the output y hat gets out of the perceptron. The output is defined by the weights associated with each edge over here, the bias at the output neuron, and something called as the activation function phi. Let's say the weights associated with the edges are w1, w2 and so on up to wn, and the bias is b. All these are real scalars by the way. The system model that maps the x's to the y hat is given over here. It is obtained by first computing the sum w1 x1 plus w2 x2 and so on up to wn xn, and then adding the bias and finally applying the activation function on top of the sum. And to get the perceptron working for a particular application, the weights, the bias, and the activation function are something that the AI engineer plays with. Some of the common activation functions that are used in AI are linear, rectified linear, commonly called as ReLU, and sigmoid. For example, the linear activation just passes through whatever it sees. So y hat in this case is simply the argument that sits inside this phi. The ReLU activation kills out any negative value to 0 and passes through all positive values. Finally, the sigmoid activation maps the real line to values between 0 and 1 using this function shown over here. As I mentioned, the choice of the activation function is left to the AI engineer and it is mainly based on the quantity that we need to output. I'll discuss how to use activations later, but for now, let me ask you some basic signal analysis questions related to the perceptron. Let's say we interpret this perceptron that sits inside this green box as a system that takes the vector x containing x1, x2, x3 and so on up to xn as the input and it gives out y hat as usual. In compact notation, y hat can be written as phi of b plus w transpose x, where w is another vector that contains all the weights in this neural network. Let's say I tell you that the weights and the bias in this perceptron are finite. The question is if you can comment anything about the linearity and stability of this perceptron system. So just take a moment, pause this video and fill out the table over here. Okay, I'm assuming that you got them all right. I'll now discuss my solution. Clearly, the system is nonlinear when a ReLU or a sigmoid is used as the activation. In terms of the stability, one can easily show that this system is bounded input bounded output, that is BIBO stable, with any of these three activations. Finally, using the linear activation does not always imply that the system is linear. This is because we have an extra bias that sits inside this expression. So to explain this, let me take an example. So let's say I use b equals 0 and phi is the linear activation function. Now clearly you can notice that y hat equals w transpose x is a linear system, right? However, when b is non-zero, the perceptron system is no more linear. Okay? So that said, let's go back to our track now. To accomplish a certain task with a perceptron, say temperature prediction, we've got to train the perceptron on a large data set. First of all, how do we even establish this data set? I'll explain this for the thermometer example. Let's say we have n number of cheap crappy thermometers that we deploy in a city. So every dot over here corresponds to a cheap and crappy thermometer. Okay. Now these thermometers give out measurements, say x1, x2 and so on up to xn, say on day 1. So the day number is denoted in the superscript over here. Okay. Now to get the true temperature, let's say I rent out an expensive thermometer on that day to get y superscript 1. Okay. The y here is to be interpreted as the true temperature because we assume that the expensive thermometer is perfect. Next, I repeat this procedure for day 2, collect data, then day 3, collect data, and I repeat this, say up to capital K number of days. After I'm done with this data collection, I can give back the expensive thermometer and save on my rent expenses, right? So now that I've established the dataset, our goal is to train the perceptron to predict the true temperature from n measurements that are coming out of crappy thermometers. Okay? Training is basically tuning the W and B over here to achieve the desired goal. And in this case, the desired goal is to make the prediction y hat k as close as possible to the true yk for every k in the dataset, right? Now, training the neural network basically requires us to answer two fundamental questions. First of all, how do we choose the activation function phi, and how do we define the notion of closeness? So, let me discuss these two questions in the context of an example where we are interested in estimating the temperature of Stockholm, a city in Sweden, and we are interested in estimating this temperature in, say, degrees centigrade. So the overall setting remains the same. We use n number of crappy thermometers and one expensive thermometer over k days to set up this data set. Okay. And in this example, let me tell you that it does not make any sense to use ReLU activation or the sigmoid activation function. This is because we do observe negative temperatures in Stockholm, and the ReLU and sigmoid activation functions can never give out any negative real number. Okay. Now, a reasonable cost function in this example is the mean squared error loss shown over here. It is simply the mean of the squared errors between the prediction ak hat and the true value ak. As the true value is obtained from the expensive thermometer, ak is simply yk, right? And as we know, a hat k, which is the estimate coming out of the perceptron, is b plus w transpose xk because we just applied a linear activation over here. Okay. So this way we are able to come up with an activation function as well as a cost function based on our own understanding of the problem. Now let's take a look at another example on how to decide phi and the cost function. The problem here is to determine whether there is a fault in a gearbox or not. As you know from the lecture on modulation, this fault can be diagnosed by simply looking at the waveform that comes out of the accelerometer stuck to the gearbox. Okay. So in this case, the input to the perceptron is the discrete time signal that comes out of the accelerometer, and the output that we expect out of the perceptron is a 0 or 1. So a 0 means that there's no fault in the gear, and a 1 means that there is a faulty gear. Okay. So therefore, naturally, the use of a sigmoid activation makes sense because the output of a sigmoid is bounded between 0 and 1. In the other cases where we have ReLU and linear activation functions, the output can blow up to positive infinity, right? Now, the question is, how do we establish the data set to train this perceptron? One way that I can think of is to collect data at different service centers that repair cars. Let's say a service center records the signal coming out of a gearbox 1. So we record this vector x1, okay? And let's say the mechanic at this service center opens the gearbox and labels it as faulty or perfect, okay? Now, we repeat this procedure for say 10,000s of gearboxes or whatever. And after we collect enough data, we train the perceptron model using something called as the cross entropy loss. Okay, so this is one cost function that's typically used in classification problems where we've got to distinguish between, say, a class 1 or class 2. In this case, it's state 0 or state 1, right? So the cost function over here makes sense, and I'm going to explain why it makes sense in this application without getting into much details of this expression. Okay, so let's say the mechanic labels yk equals 0, which means there's no fault in a gear. And let's suppose your model predicts y hat k equals 1. Okay, in this case, when you put in yk equals 0 and y hat k equals 1, you notice that 1 minus yk log of 1 minus y hat k goes down to minus infinity, and the cross entropy loss, because it's the negative of that, blows up to infinity. Okay, and this is something that's not desired, right? We don't want this cost function to blow up to infinity. Rather, we want to tune our neural network or the perceptron such that y hat k is as close as possible to 0, right? And by minimizing the cross entropy loss, we exactly do that. We avoid these situations of misclassifications. Okay. Now, having defined the activation and the cost function for the fault diagnosis and the temperature estimation problems, the only question that's left out now is, how do we fine tune the weights and the bias in the perceptron in these applications? Now, one way to solve this problem is to use gradient descent technique that minimizes the cost functions over the W and B. Okay. So in the case of temperature estimation, we minimize MSE loss with the gradient descent algorithm, and in the other case, we could minimize the cross entropy loss, right? Now, gradient descent is something that we talked about in the prerequisites, but the interesting thing here is that you don't need to write gradient descent by yourself. There are these interesting Python packages based on TensorFlow and Keras that do the job for you. These packages have made training AI models so easy that even high school kids are doing it nowadays. All you need to know is some basic Python programming, and in this example, it's just 4 lines of TensorFlow code that do the job for us. Okay, so these 4 lines just train out the AI model or the perceptron model. Okay, so I put up my Python programs on Brightspace to train this AI model and also other AI models that I discuss in this lecture. So feel free to check them out, and I hope that you can easily get started with AI based on those examples. Okay, so far we've seen the following. First, how do we choose an activation function? Next, how do we decide on the cost function to train the perceptron, which is a basic AI model? And finally, how to train the perceptron, or equivalently, how to tune the weights and the bias using few lines of tensor code. Okay, so in this section, we are going to see if AI learns the optimal weights that we already know for some problems. Okay, so this experiment, in some sense, gives us some confidence that AI works. Okay. One of the problems for which we had already computed the optimal solution is the MMSE estimator determined in a jointly Gaussian setting. If you recall, we had this equation for the MMSE estimator. Okay, it also turns out to be the LMMSE estimator due to the assumption that all the random variables are jointly Gaussian. Okay, now let's work out this LMMSE or MMSE estimator for a numerical example where we consider that 16 over 3 is the variance of the temperature random variable A, and the noise variances at the thermometers 1 and 2 are 1 and 4 respectively. Okay, so in this case, A at MMSE is nothing but 16x1 plus 4x2 over 23, right? Now this same MMSE estimator can be realized using a perceptron as follows. So the temperature measurements x1 and x2 get into the perceptron, where x1 gets multiplied by 16 over 23 and x2 gets multiplied by 4 over 23. Okay, and then these products are summed up to get A hat MMSE. Okay, note that the bias over here is 0 because I'm just trying to replicate this equation in terms of the perceptron model. Okay. Now the question is, can AI really learn these optimal weights from a training data set? So the optimal weights are 16 over 23 and 4 over 23, and the optimal bias is 0, right? So let's see if AI can really learn that. So let's consider a perceptron with just two inputs and a linear activation at the output, in which case we end up with the model of the form here. Note that the weights W1, W2 and the bias B are unknown quantities that need to be tuned. Now, to establish a dataset in order to train the perceptron, we first simulate temperature measurements based on the statistical model for x1, x2, A, n1 and n2, right? Now I'm going with a simulated dataset because I don't have enough money to rent out an expensive thermometer, and carry out a real experiment. So here, the X1s and X2s are noisy temperature readings that are derived from simulations. And A's over here are the true temperatures that are also simulated. Now, once we have this data set, we could easily train the perceptron by minimizing the mean square error loss that we already looked at earlier, right? So I did train this perceptron using just 4 lines of TensorFlow code that I put up on Brightspace. And let's call the fine-tuned weights of the perceptron as W1 AI, W2 AI, and the fine-tuned bias as BAI. Okay. Now the big question that we have now is, do these weights W1 AI, W2 AI, and the bias BAI approach the optimal weights that we already know for the minimum mean square error estimator? Okay, so let's check it out. So I started off with a dataset containing 1000 samples. Each sample contains a pair of noisy temperature readings obtained from two crappy thermometers, right? So in this case, I performed a simulation to get these readings, okay? And the A's over here represent the true temperature corresponding to these pairs, okay? Now the gradient descent algorithm is executed in several passes over the dataset, where each pass is called as an epoch. You can notice from this plot here that after about 10 passes or so, the weight W1 learned by the AI algorithm converts to 16 over 23. And this is nothing but the optimal weight in the MMSE estimator associated with X1, right? Similarly, the weight W2 learned by the AI algorithm converges to the optimal weight associated with X2, which is 4 over 23. Finally, the bias learned is also 0 after a few epochs. Okay. Now, all of these, that is 16 over 23, 4 over 23, and 0, match with the optimal MMSE estimator. And the moral of the story here is that AI can learn the optimal MMSE estimator in this example. Note that the mean square error achieved by the AI algorithm on the test set is slightly higher than that with MMSE. Okay. This is because we cannot do any better than the optimal MMSE estimator, which is easy to compute for this particular example, where all the random variables of interest are jointly Gaussian. Next, let's check out if AI can learn the map detector as well, which we saw in the class. So let's go back to the gearbox fault detection example. As you know from lecture 5, the spectrum of the acceleration signal coming out of a faulty gearbox has harmonics about the gear mesh frequency. So let's say this is the gear mesh frequency, GMF, and we've got harmonics over here. Okay, so let's say we isolate a pair of harmonics and end up with these measurement models under hypothesis 0 and hypothesis 1 that correspond to a faultless gear and a faulty gear respectively. Okay, we already know that the optimal map detector minimizes the probability of error. For the specific examples with the parameters shown over here, we can simplify out the map detection rule into this linear inequality over here. Okay. So the map detector can also be realized with the perceptron as follows. So the observations R0, R1 and so on up to R49 in this case get into the perceptron. Okay. And these are going to be multiplied by sine 0 pi over 25, sine pi over 25, etc. up to sine 49 pi over 25. Okay, and then we are going to add a bias of minus 12.5 and apply a sigmoid activation function. Okay, so you can notice that this function on the left is realized by simply multiplying out all the r's with sine n pi over 25. Okay, so we get that, and finally we add the bias, which is minus 12.5. Okay, so the term on the left of this linear inequality is realized right at the input of this green neuron. Okay, so this term sigma r of n sine pi n over 25 minus 12.5 gets into the sigmoid function, and if it's greater than 0, the network or the perceptron outputs a value that is between 0.5 and 1, and if this entire sum over here is smaller than 0, the perceptron is going to output a value that is between 0 and 0.5, right? So I can have a simple realization of this map detector with a perceptron. What I can do is, if the sigmoid outputs anything above 0.5, I'm going to detect that H1 is true, which means there is a fault in the gearbox. And if the sigmoid outputs anything below 0.5, I'm going to declare that H0 is true, which means the gearbox is faultless. Okay, so let's check out if the AI based approach converges to the optimal map detector that we just saw in the last slide. Okay, so once again I did this exercise on TensorFlow and my code is available on Brightspace. So I first simulated the training dataset by constructing the received measurements under the two hypotheses. So I once again went with a simulation based approach, as I cannot get a mechanic to examine thousands of gearboxes to find out the true state of the gear. Okay, so you could definitely build a new data set by collecting information from, say, many service centers around the world. Okay, so let's say the weight and bias of the perceptron converge to W1 AI, W2 AI, and so on up to Wn AI, and the bias converges to B AI. Okay, we are now interested to see if the parameters fine tuned via AI approach those of the optimal map detector that we just saw in the last slide. So if you go back, we explained that the optimal map detector can be realized with a perceptron where the weights are sine pi 0 over 25, sine pi over 25, etc. up to sine 49 pi over 25, and the bias is minus 12.5, right? Here, let's take a look at what I observed from my experiment. So here I sketched the 50 weights in the perceptron, okay, that had 50 edges using a solid line, okay, shown over here. And the ideal weights associated with the map detector is simply sine pi n over 25 function, which is shown by this dashed line, okay. The bias at the output neuron is shown in the title over here, okay. Now let's take a look at this video. As you see here, we start off with randomly initialized weights at the first place. Then, as the perceptron gets trained with the simulated dataset, we notice that the weights learned by AI slowly converge to those of the optimal map detector. Now, this is a very promising result, as it shows that AI can approach the performance of the optimal detector that we derived in the 19th lecture. We also notice from the confusion matrices shown over here that AI indeed performs closer to the optimal map detector. This sounds cool, right? Because we are learning something that's optimal using a purely data driven based approach. So far we've looked at how perceptrons can do several interesting things like temperature prediction or gearbox fault detection, right? Now, these perceptrons just have a single input layer comprising the purple neurons and a single output layer that has the green neuron. Okay. Multi-layer perceptrons are an extension of the concept of perceptron. They basically have a collection of perceptrons that are cascaded in several layers. For example, the multi-layer perceptron, in short MLP network, on the right has two hidden layers in addition to the input and output layers. The first hidden layer contains the green neurons shown over here, and the second hidden layer has the orange neurons. Okay. So the way the MLP network works is as follows. First, the inputs to the network are fed through the purple neurons. Then the computations are performed at every green neuron in the hidden layer. Okay. These computations are exactly same as what we saw for the case of perceptron. Next, the output of the green neurons are fed into the next layer. Okay. And this procedure is carried until we reach the final output layer. Right? So this is as simple as that. As one would expect, because of the complexity of the multi-layer perceptron when compared to a single layer perceptron, the MLP can do much more than what a perceptron can. For example, a well-trained MLP can recognize handwritten digits or even missing pixels from images. Now that we've seen how MLPs can accomplish complicated tasks, let's check out how well they work in the context of signal processing. In this section, I'm going to show you that MLPs can outperform classical techniques under certain conditions. So let's go back to the temperature example where all the variables of interest are jointly Gaussian. So here is the LMMSE estimator, which is the same as the MMSE estimator. And now let's consider two neural networks. The first one is the basic perceptron that we already looked at, and the other is an MLP with a single hidden layer. Both these networks are trained independently by minimizing the MSE loss over the training dataset. My question here is if MLP can do any better than the optimal MMSE estimator shown in this equation. The answer is unfortunately no. This is because nothing can do better than the MMSE estimator when the goal is to minimize the mean square error, right? Of course, the neural network can converge to the MMSE estimator, which is something that we've already seen in the case of the perceptron, right? But it can't do better than the MMSE estimator for this particular example, for which we know the optimal MMSE estimator. Okay? Next, let's take a look at the hard problem which had an intractable analytical solution. Here we consider the same setting except for the fact that the temperature distribution is uniform between minus delta and delta. In this case, we know from lecture 16 that the variance of this random variable, that is sigma square, is nothing but delta square upon 12, right? So I just plug that in into the LMMSE estimator here. Okay, when I do that, I get this equation for the LMMSE estimator. Now I'm going to train the same neural networks that we saw in the last slide once again for this setting. And the question now is if MLP can do any better than the optimal minimum mean square error estimator. The answer is again a no, because the MMSE estimator is the best, right? However, we don't really know what the MMSE estimator is for this setting. What we know here is just the linearly constrained MMSE estimator, right? So I just did this experiment in TensorFlow and I observed that with an LMMSE estimator, you get a mean square error of 0.7 on the test dataset. And with the MLP based approach shown over here, you end up with a lower mean square error of 0.65 on the test set. Okay. So the better performance of MLP when compared to the LMMSE estimator is because it can model a richer class of functions than the linear one. Okay. So the key takeaway here is that AI can do better than the suboptimal LMMSE estimator, that is a linearly constrained MMSE estimator, in situations where finding the optimal MMSE estimator is hard. So you notice that we just don't know what the MMSE estimator is, right? Because computing this is very hard. But we were easily able to compute the linearly constrained MMSE estimator, okay? And AI algorithms, okay, with say one or more hidden layers are better than LMMSE estimation. And the best case is that they approach the performance of the optimal MMSE estimator, whose closed form we don't know. Okay. Now let's check out another problem that is hard to solve by classical map detection. Suppose I'm interested in identifying whether a handwritten digit is a 0 or a 1. So here the observed image is the input to the detection algorithm, which is expected to output a 0 or 1, right? So let's say I want to approach this problem using the map rule. So what I do is I first start off with my hypothesis, and the first step is to determine the statistics of the images under each of the two hypotheses, right? Now unfortunately, obtaining a closed form statistics for the handwritten digits is extremely hard, and this issue propagates down to make map detection intractable. Okay, so in this problem where finding the classical map detector is extremely hard, let's try to see if AI can solve it. So in this case, what we could do is we could just use a multiple layer perceptron that tries to identify whether the handwritten digit is a 0 or a 1. Okay, and as you can notice here, AI using an MLP indeed learns to identify the digits in cases where map detection is simply intractable. So I also uploaded the Python code for this experiment on Brightspace. Feel free to check that out. That said, I'll now move on to the final phase of this lecture where I talk about how signal processing finds use in the context of AI. So let's say you're all charged up after the signal analysis course and you want to do a startup that detects faults in a gearbox. We've seen in lecture 10 that faults can be diagnosed by monitoring the signal coming out of the accelerometer stuck on your gearbox. Now, as a founding member of your startup, let's say you hire an AI engineer to work on this problem. So the next morning, this engineer comes in, extracts the sample version of the signal A1 of t coming out of the accelerometer, okay, and trains an MLP network to diagnose faults. Now, the engineer works day in and day out, and 1 week down the line, let's say your AI engineer gets the MLP to work and your system is able to diagnose faults. That's cool, right? Now, although your product works, it won't be that efficient because we did not really exploit our signal processing domain knowledge in this application. So, let me explain why this is the case here. So first of all, the sampling rate that we are using in this case is unnecessarily larger than what is really needed. I'll explain later why, but for now, let me tell you why a higher sampling rate creates a big issue. So at higher sampling rates, the analog to digital converters, that is ADCs, get expensive and consume a large amount of power. Next, you notice that the number of inputs to the MLP in just a 5-second window is about 100,000, right? And this is too large in my opinion because if you have a neural network with 100,000 inputs over here, okay, then the computational complexity can be too much in practical settings. Now, with a background on signal analysis, you could propose this system. Here we demodulate the signal by the Gauge mesh frequency, that is omega GMF, and then we apply a bandpass filter to isolate, say, the first harmonics due to possible faults. Then we know from the Nyquist sampling theory that we got to sample this signal by at least 1 kilohertz, right? So let's say we use 1 kilohertz of sampling rate. So the ADC operates 20 times at a slower rate when compared to the example that we had earlier. So in this 5-second window, you're going to acquire just 5,000 samples, and naturally we expect that the neural network is going to be smaller, right? So overall, this saves a lot in terms of money. So you move from high speed ADCs to low speed ADCs. So you save on your resources, and then you also save on battery because ADCs that operate at a lower rate consume less amount of power in real time. And you also save in terms of the computational complexity because we move to a smaller dimension neural network, right? So the punchline here is that bringing in domain specific signal processing knowledge into your problem can make AI based systems even more efficient when compared to blindly applying AI. And finally, this is my last slide on AI aided signal processing. Much of the early literature on AI has focused on software only solutions for real time inference. For example, we capture an image digitally, feed this image into a digital signal processor DSP that sends it into an MLP to figure out whether if it's a 0 or 1. Typically, all the computations in the trained MLP are done in software, which takes a lot of time. One way to speed up the processing is to implement few operations in hardware and the rest of them in software. Now, performing hardware based inference, however, brings in new challenges. For example, the weights may need to be binary. Okay, so the W1, W2, etc. may need to be binary, say plus ones or minus ones. Now, these constraints are something that an AI engineer needs to take into account while training this neural network that's going to be implemented partly in hardware and partly in software. Okay. Another interesting problem that we work on here in my group is on optimizing the weights to be applied in hardware using AI. Feel free to reach out to me by email if you are interested in any of these areas. That said, here is a quick summary of today's lecture. The key takeaway messages from my lecture are as follows. First, don't be a lazy engineer and blindly apply AI to solve your problem. As you noticed in the fault detection example, techniques that are completely based on AI can solve the problem at the expense of blowing up your company's resources. The second message is that try to develop mathematical models that explain physical phenomena and then see how classical signal processing techniques can solve the problem or even a subproblem. My third message is that try to augment AI based solutions with signal processing based solutions if possible. Thank you so much for listening and see you in the Q&A session or the exercise session this week. Bye.